Nice, thank you. Okay, so let's start a new chapter for today. So hydropower. Okay, so hydropower, I think, is one of the oldest renewable energy used to generate electricity. Okay, of course, you want to talk about which one is used in the ancient time. Actually, it's a biomass, but not used to generate electricity. But this is the first renewable energy used to generate electricity. And until today, it still have the largest share in terms of renewable energy. Okay, so just go through a little bit about the general about hydroelectricity. This is the type of the energy from the sun. Okay, again, it's from the sun because uh, the energy in the water is not by the molecule H2O, okay, but it's just by the potential energy of the water. And then the sun actually evaporate the water, which bring the water from the lower end to the upper end and create the potential energy for the water. Okay, so without the sun, we will not have any energy, any hydro energy. Of course, you may say that at the environment heating, it's still possible to have the evaporation, but I think 90% of both of the evaporation caused by the sun. Okay, the heating from the earth itself is very limited. Okay, so most of that, the hydropower is actually come from the sun. It's harnessed through the gravitational force of falling or flowing water. You need to have the falling or flowing water, then you need to create the potential energy into the water. The kinetic energy of the flowing water can also be used to spin the turbine to generate electricity. Hydropower generated 16.6% of the world total electricity and 70% of the all renewable energy. Although we know that hydropower is not considered as green energy anymore, but it's still the world largest renewable energy usage. Okay. In Malaysia, hydropower generated 17.93 terawatt hour of electricity. We have a megawatt, a gigawatt, and only terawatt. Okay, which is 11% of the total electricity generation and 95% of all renewable energy. It's need guaranteed supply of water. So before we proceed to the further, this is a water cycle. How actually the water store in the ocean. I think the ocean stores the most of the energy. Then how the water in the ocean has been moved to the hill or the upper altitude, which gives you the potential energy. So this one you can see that how the water moves up by the evaporation. Okay, so when you go up to evaporation, it will become a gas. Okay, it will condense, become a cloud, and then it will go down to the earth by the rain, or we call it as a precipitation. Okay, this precipitation, including the rain, including the snow, ice pellet, okay, all are compact under the precipitation. Okay, and then we have the sublimation. Sublimation is the transition of the substance, transition of the ice directly from the solid to the gas stage, not go through the water stage. So it's from the ice directly to the gas without passing through the liquid stage. But this only happen at a very specific condition, which have very low pressure. Okay, at very low pressure, the water vapor is easily created from the solid material. But of course, it won't happen at the sea level. It will happen at a very high altitude. Okay, and then we have the rain go down by precipitation. Sorry, the water go down by precipitation by rain or ice or pellet or smoke. And then it run through the stream, and then we harvest the energy from that. Okay. So this is how the water cycle create the potential energy. And then you can see that we have a evapor transpiration over here. This is a sum of the water, evaporation, and transpiration from the surface area to the atmosphere. Okay. Okay, then we compare between the how much of power can one dam produce. So it will be, let's say I compare the world largest dam, which is Three Gorges Dam in China, and the Malaysia largest dam, Bakun Dam. Okay, so you can see that actually its capacity is 22,500 megawatt. It definitely is very big and mostly enough to power the entire Peninsula Malaysia. But the cost is 90 billion. The height, I mean that the height in dam is about 181 meter. Split bay capacity, the water flow rate is 116,000 meter cube per second. You can imagine how much it. And then yearly production is 101.6 terawatt hour. And then actually from here you can calculate the capacity factor. Okay, let's see, we calculate the capacity factor. How much is it? 22,500 megawatt, run for 24 hours and 365 days. So the capacity factor is around 50%. Okay, it's much higher than wind energy, solar energy. And it still have the advantage to store the energy where you can use it only when needed. Okay, and then you can save this amount of oil. Okay, this one is a kilogram of oil equivalent. Sorry, ton of oil, kiloton of oil equivalent. And then the reduction of CO2, if you use the fossil fuels, this amount of CO2 you can save. Then we can see that how big is this Three Gorges Dam and how is the effect to the environment. Okay, if you look on the CO2 reduction, it's very, very huge. And then we look on the Bakun Dam, Malaysia. Bakun Dam, the capacity is 2,400 megawatt. Okay. So let's recalculate the capacity factor. It's very, very low. You notice that it's only have 607 gigawatt. Okay, only around 2.9% of the capacity factor. Why the China dam can have the capacity factor of 50%, but Malaysia, the Bakun dam only have a capacity factor of 2.9%. Okay, the reason is actually Sarawak does not need so much energy from Bakun dam. The original idea for Bakun dam is to have 30% of the generated capacity consumed in Sarawak and Sabah, and 70% sent to Peninsula Malaysia. You understand the energy from Sarawak to Peninsula Malaysia. And this plan, actually, you need to have I think the distance is about 1,700 kilometers. So you need to use undersea cable. Okay, in undersea, because of the long distance travel, we use a HVDC, high voltage direct current cable. Okay, and then you also have the Peninsula Malaysia, you have to cable 300 kilometers. So total, actually Bakun Dam is not located near the seaside. It's really quite in the rural inside the land. So to travel from the rural, from Bakun Dam to the seaside is already 730 kilometers. So the total distance from Bakun Dam to the Peninsula Malaysia, which is, I think, the target Kuala Lumpur, which have the 1,700 kilometers. So how feasible is this study? How come the government will approve this kind of project? Okay, so that actually we are not able to do it. So end up with the cable is not, we didn't make the cable. So it means that 100% of the energy generated from Bakun Dam is used in Sarawak only. Okay, and this dam is cost, it put 700 square of kilometer land underwater, because you build the dam, you increase the water level. And it's relocate more than 9,000 of the or native residents. Okay, so actually it's a very big impact to the environment, but we didn't get the advantage of the dam. Okay, so it's actually, I also don't know why they want to build the dam. It look like, yes, it's a very good idea to build a dam to generate electricity so that we don't need to rely on fossil fuels. But we still have to target and look on the supply and demand. The Sarawak needs so much demand of electricity. Okay, if Sarawak no need the demand, how you can sell the energy to other, sell to Brunei, sell to Indonesia, or send back to Peninsula Malaysia? But we have to do the feasibility study, see how possible is the things and how costly is the transfer. Okay, so okay, forget about the Bakun Dam. It's actually not a good idea to build a Bakun Dam. If the dam is located in Peninsula Malaysia, then definitely it's a very good idea. Okay, but because of the Sarawak do not have so much industry area, so we do not need so many big dam in general. Okay, hydropower in Malaysia. DNB operate 3 hydroelectric schemes in the Peninsula Malaysia with an installed generating capacity of 1,911 megawatt. You can see, we have 11 dams in Peninsula Malaysia, and the total capacity only 1,900. But a Bakun Dam alone already have a capacity of 2,400. Okay, so you can imagine that how big is the Bakun Dam. I think it's the largest dam in the Southeast Asia. They are the Sungai Perak, Terengganu, and Cameron Highland hydroelectric scheme with a 21 dam in operation. Okay, and total capacity of 5,300. Total capacity in Malaysia is 5,300. And then Bakun Dam alone is already generating 2,400 megawatt. I remember that Sarawak still have other dam because Sarawak have a lot of river. So you can easily find a good location to build the dam. Okay, why we use the hydropower? So if you compare the energy conversion efficiency, whichever relate to combustion, definitely the energy conversion efficiency will be very low. Because once you do the combustion, at least half of the energy will be converted to heat. And then only a few, maybe 30% converted to mechanical energy, kinetic energy. Okay, so whichever use the combustion, definitely the efficiency will be very low. And then for this dam, we just use the potential energy of the water to rotate the turbine. So the efficiency can be at 90%. So it's actually it's a very good high efficiency compared to the rest. There are two main parameters we need to consider in the dam, which is referred to the parameter affecting the output, which is the head and the flow. We don't call it as a height, but we call it as a head. Okay, head and flow are the two most important things in hydropower. Head is water pressure. Okay, we measure the pressure in terms of head, but not in terms of Pascal, because it will be, I think it's easier to remember and record. Okay, so as we know that one atmospheric pressure equivalent to how many meter of water? Anyone can tell? Atmospheric pressure, 1 atm or 1 bar, equivalent to 100
meter.
No, equivalent to 100 kilopascal and equivalent to 10 meter height of water. Okay, so it means that 10 meter height of water will give you pressure of 100 kilopascal. Okay, so they calculate in this way. But of course, the pressure depends on the density and height. Okay, so for the density of water, it's referred to the 10 meter height. But let's say you use a mercury. Mercury is 13.6 times more dense than water. Okay, so it's just around, I remember it's around 76 cm. Okay, this is 76 cm. 76 cm height of the mercury equivalent to the 10 meter height of the water and equivalent to the 1 atm, 1 atmospheric pressure, or 1 bar, or 100 kilopascal. This so you have to know the unit conversion. But normally the mercury we seldom use. So this one definitely we will use in terms of water only. Okay, 1 atmospheric pressure equivalent to 10 meter height. Okay, maybe I give you one scenario. For those who actually have the aquarium at home, let's say you use the water. Okay, how you want to pump out the water? You let the water flow out without the pump. Okay, so normally we put a pipe like this. Okay, and then we shut it. Okay, so make this part empty with our vacuum. So the atmospheric pressure will press on the surface of the water and then push the water to flow through this pipe and flow outside. Okay, and this is the typical method we use to pump the water flow outward. But this only applicable for the height of 10 meters. So if the height is more than 10 meters, you are not able to pump it. So it means that atmospheric pressure here will press, maybe I draw it higher. The atmospheric pressure here able to push the water up to 10 meter height only. Beyond this, you cannot do anything. Actually, it's not suck, actually it's a push. It's not sucked by the vacuum. Vacuum cannot do anything. But it's a pressure from the outside atmosphere, press it, and then you go up to 10 meters. So this method cannot be applied at the height more than 10 meters. Okay, I mean that the pump height, the pump height cannot be more than 10 meters. So this is a reason, this is a definition of the 10 meter height. Height is the water pressure, which is created by the different equation between the water intake and the turbine. Heat can be expressed as vertical distance, feet or meter, or as pressure, pound per square inch, PSI, or megapascal. Okay, PSI we seldom use. Normally, if you go to the petrol station, you want to pump your car tire, then you see PSI and megapascal. Okay, but PSI we seldom use pound per square inch. We always use a megapascal, which is the SI unit. Net heat is the pressure available at the turbine when water is flowing. Heat is the water pressure. Net heat is the net water pressure, because when the water is flowing, the pressure that it creates will be lower, according to the Bernoulli principle. The higher the velocity, the lower the pressure. Okay, so the flow will reduce the heat. So in this case, the heat will be low due to the flow. That's why we call it as a net heat. Okay, then we talk about the flow. Flow is the water quantity per unit time. So it's mean that flow rate. So in terms of meter cube per second. Okay. Okay, this one they have a gallon per minute, liter per second, cubic meter per second. Both head and flow must be present to produce water power. And then flow, we do not have the net flow, but we have one term called design flow. Design flow is the maximum flow for which your hydro system is designed. So we set the design flow accordingly to the flow rate of the river. Okay, let's say your flow rate of the river it changed from 5 meter cube per second to 10 meter cube per second. So your design flow must be in between 5 to 10 meter cube per second. If you set your design flow higher than 10 meter cube per second, then it means that your power, your system will be under utilization. You won't fully utilize the system because you always have less water. Okay, the maximum flow rate of the river only 10 meter per second, 10 meter cube per second, but you set your design flow for 12 meter cube per second. So of course, it will be under utilization all the time. Okay, so you have to choose properly. You can choose below 5 or choose at 5. If you choose at 5, it means that your system, your hydropower system will operate at 100% capacity all the time. But you will waste a little bit of the water. When the water is too high, you cannot use it because it's limited by the system capacity. Okay, so it's very important to make your design flow. Of course, the guideline will tell you that design flow should be how many percent exceeded from the total flow or from the minimum flow. Okay, you can use the standard value, they calculate, or maybe at a certain condition you want to custom it, also can. Maybe your consideration is just to fully utilize the turbine, then okay, you can set a low design flow. Net head and design flow are used to specify the hydropower component. And we know that, okay, why flow and head is important. Then we look on the equation. Equation available in the water. So it's come from the energy, potential energy. Potential energy, we have the equation of M, G, and H. Okay, mass times gravitational times the height. This is the mass of water, of course. Okay, but you want to find the energy, power. So the mass now will become the mass flow rate. It means that the change of potential energy per time. Okay, mass flow rate, GH. And then the mass flow rate is quite difficult to measure. We can convert to the volumetric flow rate. Okay, which is rho times the Q. Volumetric flow rate, density times the volumetric flow rate, and H, and what else? G. Okay, so rho G H2. So we can see that rho of the water is the density, is a constant. Gravitational force, constant. So we can say that power of the water is always changed with the height and the flow rate Q. Okay, we can get this P equal to rho G H2. And then the unit will be in terms of what? The direct forward comes from the potential energy. Okay. Then we move to the next one. Let's say we try one example using only this equation. A group of TAUC researchers plan to install a hydropower to provide electricity at Lata Kijang waterfall. I think it's the tallest waterfall in Peninsular Malaysia. The stream of the water runs down the hill to Tapa, where it can construct a simple hydropower installation. So the effective height is 25 meters, and the water flow through the system at the rate of 2.5 meters cubed per second. And the simple inexpensive hydropower has a working efficiency of 85%. So you need to find how much energy can be generated with this system per year. Okay, based on your own understanding, you can calculate first. Okay, so we start from A. So of course, to calculate the power will be rho G QH. Okay, but not 100% of the power in the water can be converted to the electricity. So you have to consider the efficiency of 85%. Okay, so times 0.85. So you will get flow rate 0.5. Make sure that everything is as a unit before you calculate. $104.23 kilowatt. Okay, so a simple hydropower station, I can generate 104.23 kilowatt of the energy. Okay, so how many houses Sorry, wait, let me calculate first. Because we do not want the power, we need the accumulated energy. Okay, this is just a power. Okay, then you can see that how much energy can be generated in the system per year. Okay, so to get energy is a power times time 104.23 kilowatt. How much time you have? So you can get the unit in terms of watt hour or in terms of joule. But it seems like the question B they give you kilowatt hour. So maybe I can just let the answer in kilowatt hour. So time I have is 24 hours a day, and for 1 year, 365 days. So the total energy can be generated is a 930 megawatt hour. Okay. So based on this amount of energy, how many houses should this energy support? Assume that an average community consumption is actually 12,000 kilowatt hour per year per house. So what if I forward? We take the total energy divided by energy usage per one family. Okay, so 76.088. So we have to round up to 76. Round down, okay? Then part C, how much oil would be required in an oil-fired power plant to generate the equivalent amount of electricity energy as hydropower generated in a year? Okay, the energy content of the oil is 11,630 kilowatt hour. So you want to generate this amount of energy. How much energy you take? Okay. Uh, so number three, we take 913 megawatt hour divided by the energy content of the oil 11630 kilowatt hour per ton times the efficiency of 35%. So you will save the amount of the energy. Okay, 224 tons of oil. Okay, number D. How much CO2 emission would be if the oil power plant was used? The oil power plant produced 0.27 kg CO2 per kilowatt. Okay, so for this case, it's very direct forward because some of you are not from the chemical background. Okay, from EE background, I think maybe the background chemical is not so good. So I just use direct method. So to generate 1 kilowatt hour, you will generate 0.27 kg of oil. So you want to generate 913 megawatt hour. So 913 megawatt hour divided by 0.27. Okay. Sorry, it's times. So it means that I can save 246.527 tons of CO2. Okay, but this is not always the method. Supposedly, how we want to solve this. Okay, so for example, let's say oil. What is the chemical composition of oil? Let's say I have the oil of C. Normally, oil have the chemical formula of the carbon, hydrogen, and oxygen, or maybe just carbon and hydrogen. Let's say it's carbon and hydrogen. Okay, and to complete the combustion, okay, CH18 plus oxygen, and then you apply heat, you will burn. So you will generate CO2 and also H2O. If given that this is a complete combustion. Okay, now you want to balance the C and HO here. So first, you have Ca. Okay, so you need to have the HCO here to balance. Okay, same thing, you have to H18. So you need to have the H18, 18HO here, and also C. Sorry, carbon. Okay, so carbon is that balanced now. So we have 16 plus 9, 25. Oh, so this should be 12.5. Okay, so it means that 1 kg, 1 mole, we call it 1 mole. 1 mole is calculated in terms of the number of molecules. 1 mole of the oil will generate 8 mole of carbon dioxide. Okay, so based on this, you can check 1 mole of oil equivalent to how many kg of oil, and 1 mole of the CO2 equivalent to how many kg of CO2, based on the molecular method. And this is only the correct method to calculate. So it means that different oil will give you the different output. Okay, but the equation must balance. Okay, we don't care about how much oxygen we use, but we care about how much CO2 released to the environment. Okay, this is I think you learned in the secondary school, I guess, if you still remember. Okay, then we talk about the type of hydropower. In general, we have 3 types of hydropower. Actually, we call it 2 types. The pump storage hydropower may not be a real hydropower. Later, I will explain. Okay, first one is a run-off river. Okay, it means that you do not have the dam. And the storage hydropower, where you need to construct the dam. And then the last one is a pump storage hydropower. Pump storage power provides a big load supply and harness water which cycle between the lower and upper reservoir by pump, which use surplus energy from the system at time and low demand. So maybe I can have a look at this. Okay, we start from run-off river hydropower. Okay, this mechanism of run-off river hydropower, you can see that I do not actually fully block the flow of the river, but I just use a partial of the water to go through the turbine. Okay, so it means that this facility channel the flow from the river through a fan stroke. This is what we call a fan stroke on the pipe to spin the turbine. Okay, and this one is totally no storage, or maybe you just need a very minor flow storage a little bit at the front. Okay, but normally it's not needed. just to make sure that the flow is going into the tube, the pipe, the band stroke we put now. And because of no dam, so you will not increase the water level at the upstream. So we will have the less environmental impact to the surrounding. Okay, so you can see that the water level still remain the same on the upstream, but water level at the downstream will reduce. So reduce in terms of water level, the impact is not so high compared to increase the water level. Because you increase the water level, you will submerge some of the tree or jungle in the water. So when the tree decompose by the microorganism, they will release the carbon dioxide. So in other words, you release the carbon dioxide in the environment. But you decrease the water level, actually it's just maybe the river ecosystem will be affected. Okay. So that because of you reduce the water level, because some of them has been used to go through the power station. So the water level at the surrounding will reduce. Okay, it will affect the water veracity and depth, and maybe affect the river ecosystem, the fish and aquatic organism. Okay, this is the normally you have to operate at where you have very high height, you have very big heat, maybe in the hill, so that you do not need to create the dam to generate the height, to generate the pressure to push the water flow through the field. So in case of the how to say, the slope is not very deep, not very big. Okay, let's say just 10% of slope. Then this runoff river hydropower may not operate at very good efficiency. Remember that when the water passes through the tube, the penstock, there is a friction. So the friction will eventually reduce the amount of energy you have in the water. Okay, so if the slope is lesser, so it means that the flow of the penstock will be longer. Okay, and now it will reduce the total efficiency of the power system. So normally this runoff river system is more efficient to be used at where have the bigger slope. Okay, bigger slope, the height, I mean that between 0.1 and 0.3, they have a very good elevation. Okay, very high, very big height difference. Okay, and actually it's quite seldom used and rarely used in the commercial system because the power generated from the system normally is quite low. Maybe you can build just to power a rural village. Okay, but to generate a commercial power plant, normally we will not use a runoff river hydropower. The power output is relatively low. Okay, so second one is called storage hydropower. Most of the commercial hydropower system actually using the storage hydropower. So first thing, you need to build the dam. Okay, so the dam must be built on the where you have the large drop in elevation, very big height difference. But where you can build, you can see that mostly you build in between the mountain. You have two mountains and then build the dam between them. Okay, this is not because of the height, but because of to save the material. Now you want to make a reservoir. Okay, so we have to minimize the amount of the material used. Okay, so they normally the dam, the reservoir will build at where you have very narrow opening. Okay, so in the narrow opening, of course, the wall that you need to build, the dam that you need to build is much smaller. Okay, at the same time, you need to cover the entire area because the other area will be blocked by the mountain. There's only one flow, one path to flow out. Then you block the path. Then this is the best idea. Okay, so you build a dam to increase the water level. So you will store a lot of water behind the reservoir. Okay, depends on the rainfall. Right? Okay, and then we have intake in near the bottom of the dam. Okay, and then go through the penstock and rotate the turbine. Okay, so you can see that we have uh, height difference over here, which will turn the turbine and generate electricity. So after the water turn the turbine, it will release the river at the downstream. Okay, and then when the generator is being turned by the water, it will generate electricity, and you can connect to the grid. The system is look simple, but every construction of the dam of the turbine system is actually quite complicated because it's a very big scale. Okay, and you also notice that the dam is normally in this shape, triangle shape, which the wall thickness will be very thick at the bottom and very narrow at the top. This is because water pressure at the bottom is much higher than the water pressure at the top. Okay, so you must build in this way. At the bottom is very thick. At the top, you don't need so much material. Okay. Okay, this is the operation of hydropower plant. I think it's the same as I explained this one. Okay, then we look on the what is a good advantage of this storage hydropower. Typically, a large system that uses a dam to store water in the reservoir. Then electricity is produced by releasing water from reservoirs. Okay, like this one. Okay, yeah. There's one very special advantage of hydropower compared to other type of renewable energy is storage hydropower provide base load as well as the ability to be shut down and start up at short notice accordingly to the demand of the system. It can be as a base load because you can control the output. You store the water in the dam. So whenever you need, you can just adjust the number of turbine. Normally a dam have a few turbine. Let's say you have 4 turbine. Okay, so it depends on the demand. Then you can choose to operate 1 turbine, 2 turbine, 3 turbine, or 4 turbine. Okay, and the output will be very consistent. Not like a wind turbine, not like a PV photovoltaic. The output is totally depends on the input. But this one you can control it because you have the storage. Okay, storage in terms of water. And then it has the ability to be shut down and start up at short notice. This one same thing. Let's say for renewable energy, PV photovoltaics and wind energy, we are not going to start up and shut down always. We will generate, we can capture as much energy as possible because we have no storage. And then for the fossil fuel power plant, which need the combustion, you are not able to shut down and start up easily. Okay, because to reach the optimum efficiency, you need to maintain at a certain temperature and pressure. But this is not so easy to get. Maybe after 2 hours of operation, you only can get a stable operation, which at the optimum pressure and temperature. Okay, so you need a few hours to get it stable. But this one, hydropower, as long as you let the water to flow through the turbine, it's already stable. So it has ability to shut down anytime. And it can start up anytime, just as you like. And it always will operate at the maximum efficiency. Maybe just to take a few seconds to operate. Okay, so to go up to the maximum efficiency. This is the advantage of hydropower compared to the different other type of the combustion power plant. Same thing, all that combustion power plant is quite complicated. They need to control the pressure and the temperature. Okay, so they can combust at the best condition. At different temperature, different pressure, you need a different amount of fuel, different amount of oxygen. Okay, so the control is quite complicated. If the amount of oxygen input is not correct, then you will get the incomplete combustion. Okay, it can offer enough storage capacity to operate independently of the hydrological inflow for many weeks or even months. So it means that the storage normally able to operate independent to the weather, whether you have rain or no rain, never mind. Because the dam is big enough to operate without any rain for many weeks or even months. Of course, it depends on the capacity of the dam you have. Okay, so it's always a very good advantage of storage hydropower. Okay, now we try to learn about the measurement of the head of hydropower. So let's say this is a hydroelectric dam. So I have point A, B, C, D, and E. How do we measure the head? Is from A to B, A to C, A to D, or A to E, or maybe C to E? Any idea? Maybe think about it. Long time didn't take attendance. Okay, so this should be the attendant. I gave you 5 minutes together with the short break. You give me the answer. I will give a poll over here. So we have few options. A to B, A to C, A to D, A to E. What else? Maybe intake to C. Okay, so you try to vote for your answer. Remember, even you don't really know, also speak what is related to as attendance. And I will do the summary at 11:53. Okay. Okay, just look on the result. So I think A and C have the most number of what? 18. Okay, B, C, and A, B is quite a lot. Okay, let's discuss. Okay, A, B, C, D, E. All right, forget the word. A, C. A, C. Very less number of you get the correct answer. Okay, the actual answer is AE. Okay, the correct answer is AE. I think only 4 of you choose the correct answer. AE. Okay, why? So first, you look at here, A, B, C, D, E. So we want to measure the heat applied on C. Okay, but the problem is there is a heat grade between point A and point C. Okay, which to push the water out. But at the same time, they also have the water heat between point E and point C, which to push the water in. Okay, so in other words, you want to see the pressure difference at point C, you should take AC minus EC. So that the only heat you have is actually AE. Maybe I give you another scenario. This look like a U tube. U tube. Filled with water. Okay, this water. And then this is the turbine. Okay, and then water level at E is over here. So that because of the heat difference, height difference, the pressure to push the water flow through the turbine go to point E. And can you imagine that what if the water level at this is E? Water level at E and water level at A is the same. Do you think that the water still will push through the turbine C? Definitely not. Okay, because both sides they have the same pressure. So we have to calculate the net pressure. So definitely the C will not move anymore because both sides have the same pressure. So to get the net pressure, we should take A minus the water level at E. Okay, this is the correct condition. But this also has some kind of system, something like this. Point A, point C, and point E. The water level at the outside, the river, is much lower than in the land. I think this is the most of the case. They will be in this way. Okay, you will pass through the line, and the water level at the downstream is actually very low. So in that case, you cannot take A minus E anymore because the C is over here. So the head on the turbine is only A to C. Okay, although that you still have the head over here, C and E, but it won't affect the turbine. Okay, but it's higher than C, then it will affect the turbine. Okay, can you see the difference? So the water level at downstream is a very important parameter as well. Okay, so in terms of water level increase, then the heat that you have in point C also will reduce. So that actually the power output will also reduce. Okay. No question. Huh? Then we talk about the pump storage. Pump storage is where you use the turbine or pump to pump the water at the daytime. At the night time, sorry. Okay, you can see at the daytime, the water pass through the turbine, rotate the turbine, generate electricity. And in the night time, you use something to power the pump to pump the water upward. What can power the pump? Are you going to use the oil or fossil fuels to power the pump? Definitely not. Because you want to use the oil to power the pump, why not I just burn the oil at the daytime to generate electricity? Okay, because remember that when you do the conversion, some of the energy you have lost. So we try to minimize the number of conversion. Okay, so what kind of energy always available at night, but not in the daytime? But if not harvest it, then it will gone. It won't store it. Any idea? How we want to power the pump at night? Yes, wind energy. Okay, wind energy normally we have a stronger wind at night. Okay, so that stronger wind at night, but do not have the demand. We do not have the demand at night. Okay, all the factory maybe it's not operate for 24 hours, just at the daytime, 8 to 5, 8 to 6. So that at night time, you have excessive energy, then you can use to power the pump. Okay, so normally this system is attached to the wind energy, wind turbine. But this is considered as a wind energy or hydro energy. Okay, I would say that the natural is come from the wind, but the mechanical used is hydro. Okay, the mechanism definitely is hydro, but the origin of the energy is come from the wind energy. Okay. Okay, then next we talk about type of turbine. There's many types of turbine. So how you want to pick the most suitable pump for your system? So in general, we have 3 types of turbine: impulse, reaction, and gravity turbine. Impulse and reaction is quite widely used. Gravity turbine is not really used for electricity generation. So impulse turbine, if you read the word impulse, so it means that you use a very high velocity jet to push the turbine to rotate. You give the impulse in terms of water, okay, something like jet lamp, high velocity jet to rotate the turbine. Okay, and secondly, we have the reaction turbine. Reaction turbine is mean that you have a very high flow rate. Okay, this flow will pass through some aerofoil blade of the hydro turbine and then create the pressure difference which impose the lift force and rotate the blade. This is what we call it reaction turbine. In reaction turbine, normally you will be fully immersed in the water. Okay, and then for gravity turbine is use the weight of the water to rotate the turbine. It's more direct forward, simple, but of course you will not get too much energy output because you just use the weight, okay, but not use the pressure. So we will go through one by one impulse turbine. Okay, have a look on impulse turbine here. So here we have 2 types of impulse turbine, which is a Pelton and turbo. Pelton is a more well-known impulse turbine. Okay, it's driven by a high velocity jet or multiple jet of water. You can see that the jet of water push on the cap over here, over the turbine, and rotate the turbine on the van and blade. Okay, this one we call as a Pelton turbine. And then you can see that actually the cap is something like this, something like crab. Okay, so you can see that there's an opening at the back, just to allow the continuous. After you push on the front blade, you go to the second blade. Okay, or cap. So you have to continuously push on the blade to rotate. This is the idea. So we push on the blade to rotate. And then second one we call it as the turbo. Okay, the only difference is that the turbo has the jet enter about a certain degree, maybe around 20 degree, to the plane of the rotation. This one you can see that is a 90 degree. Okay, start rate, push on the brake and rotate. But for Pelton turbine, one time it can only hit on one blade or one car. But this turbo turbine, because it's entered at 20 degree at the side, so it's made possible to use a larger jet related to the turbine pitch diameter. It can handle more flow rate per time. Okay, so if you have the higher flow rate, then you can consider using turbo turbine. Okay. So this is a difference between them, not so it's turbo or what. But actually, because of the angle, you can see that the angle is not perpendicular to the rotation. So in the term of force input, it should be have the slightly reduction in efficiency for turbine. Okay, so I would say that Pelton should be the higher efficiency, but it can support only low flow rate. But turbo, it has a slightly lower efficiency, but have the more power output because it can handle more flow rate at the same time. But of course, the angle is not, the efficiency affected by the angle is not very significant. So in the actually practical world, how to say, the bracket profile, I mean that this cap profile, okay, and the material make more different in terms of the angle. Okay, how we want to make increase the efficiency actually depends on this bracket profile. How you want to design it. You can see that the bracket has a specific design, have an opening. How big is the opening is needed. And you can see that there's a center line. So they will split the water jet into two parts, left and right. Okay. The ideal case is the water jet have to hit on the blade. Okay. So when it hit on the blade or bracket, it must be perpendicular, so that you will get the maximum rotation torque. Remember that torque is a perpendicular force times the distance, times the radius. Okay, so the angle when hit on the bracket is very important. Secondly, you do not want once the water hit on the blade, on the bucket, what happens? It will refract. Okay, of course you hit it, Newton's third law, it will refract back to the opposite direction. And that refraction may affect the water income. Okay, so you need to design so that when it hit on the blade, it's continuous, 90 degrees. When you want to refract, you don't let it to refract outward. You have to refract to the downward or somewhere else, but not to the opposite direction to the flow, or else it will reduce the velocity of the flow. So it's make it, when hit the blade, I want to hit it like this, hit the blade 90 degrees. But Newton's law, it will reflect back to the opposite direction. But you need to design the blade properly so that when you hit it, it's 90 degrees, but when it release the water, going downward. Okay, so the design of this bracket is very, very important. Maybe a lot of study can be done on that. Maybe it can be a final project or what, I don't know. Maybe you can study on the bracket. How does the bracket design will give you more power at the same input power? Okay, so this is Pelton and Taco. Pelton hit the blade at the 90 degree, and turbo is actually come from the 20 degree from the side. Okay, there's an advantage and disadvantages. And the third one in power turbine we call as a cross flow. This cross flow turbine is not entirely immersive product, but used in low head and high flow system. The water passes through the large rectangular opening to drive the turbine blade in contrast to the small. Okay, so you can see that inlet, because of the water have low head. So if low head means that you do not have enough pressure. So you need to press on a few blades at the same time. Not like a Pelton, it's only push on one blade per one time. This one, you will push on 4 to 5 blades at the same time and for 2 times. You can see the first time, the stage and second stage. So we make the flow to rotate in the same direction. Okay, but this one is not very widely used like cross flow. Normally, Pelton and the Taco is more widely used for the impulse turbine. Okay, the next one is called reaction turbine. Reaction turbine, French turbine is the most widely used water turbine today. Okay, and this type of reaction turbine. So you can see that an inward flow reaction turbine that combines the radial and axial flow concept. French turbine is the most common water turbine used today. So it combines the radial and axial flow. Later I will show you how it's combined. And this is actually a type of turbine that developed torque by reacting to the pressure or weight of the fluid. They use the weight and pressure of the fluid, and the operation is actually using the aerofoil theory. So it means that it create pressure difference, it create the lift force, and then to rotate the blade. Okay. And this, okay, before we look on the Kaplan turbine, we look on the Francis turbine. Okay, so the flow will go in from the side, or we call it as a radial flow. Okay, pass through the turbine and go downward. So it becomes axial flow. So go in by radial and go out by axial. Okay, and now we have the new one called Kaplan turbine, which is similar to the Francis turbine, but now it has the movable blade. The blade able to adjust accordingly to the flow and pressure. Okay, it has an adjustable blade to achieve efficiency over the wide range of flow and water level. So it will be more complicated because the blade must rotate, the angle of the blade must rotate to get the higher efficiency. Okay, supposedly this Kaplan turbine have the higher efficiency, but because of the moving part, because the blade must be moving, so the cost also will be higher. I remember that at most of the situation, the flow rate and head is quite consistent. Okay, so we not really need to use a Kaplan turbine, which cater for the different flow and water level. We use the Francis turbine, good enough for many of cases. That's why this Francis turbine is the most common used water turbine. Cheaper and definitely good enough for the standard water level and flow rate. Okay, maybe all the certain situation where the flow rate and water level keep changing, then we can use a Kaplan turbine. This Kaplan turbine allow efficiency power production in the low head application. So whenever you have the low water level, then you can use a Kaplan turbine. So how we do it? You can see that the blade of Francis turbine is something like straight. Okay, so if the head is very low, so the water, because the opening is very big, you can see that the opening is very big. So the water will just go through the turbine and then go down. You won't rotate the turbine. Okay, it will flow out through the turbine, but the turbine is not rotated. Remember that turbine is connected to a generator. You need a quite very high torque to rotate the turbine. So if the head from the water or the pressure of the water is too low, then you cannot rotate the turbine. But for this Kaplan turbine, it's very easy. Yes, now the head is very low. So I change the blade angle. Okay, I make it flat. So make it flat something like I close the opening. Okay, so no choice, the water have to press against the blade to go through, to flow downward. Okay, so that in this case, you stay able to operate at the low head condition. Even low pressure, you also can use the Kaplan turbine to generate electricity because you can adjust the blade so that the opening becomes smaller. And then the water you will force to pass through the blade and generate the lift force. And do notice that this one, when you go to the turbine, it's actually the axial flow. It's already the flow downward. Okay, but for this Francis turbine, when you go to the turbine, it's a radial flow. And when you come up, it's axial flow. Okay, so that we can say Francis turbine is a combination of the radial flow and axial flow. But for this one, Kaplan turbine, it's always the axial flow. Okay, go in and out is both axial flow. So this is the difference between Francis and Kaplan. And maybe in terms of outlook, it should be like this. Okay, Kaplan turbine, you can see this one you can rotate the blade. Okay, and then Francis turbine is a fixed blade. Okay, and this is a comparison between the Francis and Kaplan turbine. So you can see that Francis turbine have lesser efficiency because you have the fixed blade, you cannot control the angle of attack accordingly to the flow rate and the pressure head. So Kaplan turbine high efficiency, type of flow is a mixed radius of action, okay, and losses are higher, okay, because angle is not correctly adjust based on the water level, and the size normally larger. And this one is more compact. And the head, normally we need higher head to operate the Francis turbine than the Carbohydrate turbine. Okay. Okay, the next one is called gravity turbine. You can call Archimedes screw or overshoot water wheel. So we just use the water density, the weight of the water to rotate the blade. Okay, you hold the water and then the weight of the water will rotate the turbine. And normally the efficiency and the power output is quite low. Normally it's not for power generation, but just to rotate the pump or whatever. Okay, it's a quite traditional method of usage of this hydropower. And this is a turbine classification. So you can see that we have different head classification. So which type of turbine can be used? So below, more than 50 meters, you can use Pelton or the tugboat, which is a very high head. And medium head, this is a turbine that you can use. And low head, this is the turbine you can use. You can see that gravity turbine only applicable for low head. Even high pressure, no use. You notice that the intake is just a water flow. If the pressure high, then you will just pass through the turbine. Okay, you can see that if water pressure very high, it will flow very fast. So you just go down, lower. You won't rotate the turbine. Okay, so that this gravity turbine normally only applicable on low head, which is not suitable for power generation. Okay, and then if we look on the more detailed picture, yeah, this one is between the head and flow. Okay, so this we have 6 type of turbine over here. So let's say at the head of 50 meter, flow of 10 meter cube per second, then what kind of turbine you can use? So you can based on this figure, this graph, to identify which type of turbine you can use. Okay, so let's say this one I said 50 meter head and 10 meter cube of second of flow. So it's really this one. So you can use Francis turbine, you can use the Carbohydrate turbine. Okay, this two only. The tugboat is just at the end already, so normally will operate at a very good efficiency. Okay, so you can use Francis and Carbohydrate at this case. You can base on this one. And then another thing that other than head and flow, you notice on this power, the diagonal line, 10 kilowatt, 50 kilowatt, 100 kilowatt. Okay, so you can see that Francis turbine is normally operated at a higher power. It means that it's a larger scale, up to 10,000 kilowatt. Okay, but some of the turbines are not able to operate at a high power. For example, cross flow up to 1,000 kilowatt only, but Francis get up to 10,000 kilowatt. It can be 10 times higher. Okay, so you have to consider, let's say our type of turbine, what is the power output, what is the head and flow that you have in the system, then you will choose. Okay, but the head here, of course, the net head, and then the flow here is the design flow. It's not the flow of the river. Okay, so this is the best guideline to choose the type of turbine. But of course, this is just a general guideline. Francis turbine also have different type and also come from different manufacturer. So you should always refer to the specification given by the manufacturer. Okay, for example, something like this, they'll give you the minimum flow range for that kind of turbine. Okay, for example, Francis turbine, minimum flow range is 0.5 meter cube per second. Below this, Francis scale turbine cannot be used. And then maximum flow range, 900 meter cube per second. You can see the range is actually very, very huge. And compared with other type of turbine, the flow range can up to 900 meter cube per second. But you can see that Pelton, tugboat, is just 60, 10, 50. So comparatively very, very low flow rate. Okay. And then the minimum head. You can see that Pelton and tugboat is actually the impulse turbine. So you need a higher head to operate. So at least 50 meter of head. Okay, and maximum get up to 1,000 meter of head for Belton turbine. Okay, and Francis turbine is already can operate at 10 meter head. Okay, and you can see that we have this optimum flow accidents. What's mean by flow accidents? So flow accident is the percent of time that the design flow is accident. What's the meaning? Okay, something like this. The water level is keep changing. Okay, changing from 5 meter to 10 meter, 5 meter to 10 meter for all the day. Okay, so that let's say my design flow is set at 8 meter. Okay, so some of the time the water level will be more than 8 meter. So this one we call as a flow accident. How much is exceed more than that? And we count in terms of percent, how many days of time. Okay, in terms of day, in terms of hour also can, as long as in terms of time. Okay, so it means that for, let's say for cross flow, the optimal flow accident is 10%. So it means that, let's say that the maximum flow is 100. Okay, so your design flow should be just 10%, maybe just 90, yeah. Okay, so just 10% of the time, the flow will exceed the design flow. Okay, this we call it as optimum flow accidents. Okay, and then the next one is the ratio of the minimum flow to design flow. This one also same thing. You measure the minimum flow to the design flow. So it means that from here, you already can know that agak-agak design flow is how much. Minimum flow is 0.05. Okay, and design flow should be 33%. So it means that 0.15. Okay. Let's look on this example maybe. This is the flow duration curve for a small hydro scheme with a net head of 4.6 meter and design flow of 2.7 meter cube per second. The peak power output of the scheme is 88 kilowatt, and the annual capacity factor is 58%, and the turbine has a hydraulic efficiency of 54%. Okay, so you answer 1, 2, 3, 4. Maybe give you 2 minutes to go through it before we discuss. First question, indicate the percent of time that the design flow is accident. So the design flow, okay, the design flow is given 2.7 meter cube per second. So 2.7 meter cube per second is at where? At here, you see. Can you, okay, do you understand the graph? You can see that this is the flow rate against the time accident. So of course, at a very high flow rate, the time accident should be lower. So it means that in 1 year, okay, let's say we take 17. Let's say the flow rate is 17. Okay, so in 1 year, 3% of the time, the flow rate is more than 17. Okay, can you understand the concept here? So let's say I take at the flow rate of 1 meter cube. So let's say here. Okay, so it means that 60% of the time, the flow rate is more than 1 meter cube per second. This is how we read the graph. Okay, and then you always have the 2 lines. One is called total flow, one is called the available flow. Okay, so total flow will be different from available flow because how to say, some of the flow will be restricted by the environmental or legal condition. maybe some of in terms of how much water you can release to the downstream per unit time for flow rate. Okay, so that you always have the total flow and available flow. You have to available flow to be total flow minus some restriction by the environment or legal condition. We do not know what kind of the government rules will set. The flow rate cannot be more than 80 meters per second, or maybe at a certain time you cannot release the water to the downstream. Okay. So now the question indicate the percentage of water that the design flow is exceeded. So design flow is 2.7. So we draw the one line from 2.7. 2.7. So I think it will be around here. So cut through the red line at 30, and we'll cut through the dotted line at maybe 50. Okay, so I can answer it this way. They ask for the percent of time that the design flow exceeded. So which is 13% of the time, the available flow will be more than the design flow. And 50% of the time, the design flow will be more than the total flow. Okay, if you only have one line, okay, like two lines, then you explain both lines. Total flow and available flow. Okay. Okay. So this one, you have the available flow. %. Total flow 50%. Okay, can I follow? Okay, next. Calculate the total efficiency of the scheme. Efficiency is output over input. Okay, so what is the output? It's already given. The peak power output of the scheme is 88 kilowatt. So output is 88 kilowatt. Okay, how about the input? So the input should be from the head and flow of the river. Okay, so it should be rho G QH. Okay, so the total efficiency is 0.722 or 72.2%. Okay, do you notice that the question gives you the hydraulic efficiency of 84%? Hydraulic efficiency is not referred to the total efficiency. Hydraulic efficiency is defined as a ratio between the power given by the water to runner of the line and the power supplied by the water at the inlet of the line. So it means that how many percent of water can absorb by the turbine. Okay, it's what we call as a hydraulic efficiency. But the total efficiency, including the conversion to the transmission to the grid, okay, including the generator efficiency. Okay, hydraulic efficiency just depends on the turbine itself only. How many energy of the water can absorb by the turbine, and then the energy from the turbine will rotate the generator and produce electricity. Okay, so that the total efficiency normally will be lower than the hydraulic efficiency. Okay, so it just confuse you by giving you this value, but actually we not use that in the calculation. Okay, number 3. Calculate the annual energy produced. Okay, so annual energy production. So you can see that the peak power output is 88 kilowatt, and it gives you the capacity factor is 58%. So that the annual energy produced will be 88 kilowatt times only 0.58. Okay, so here we can know that not yet, time 0.58, we only get the power, but you need the time 24 hours and 365. This is not related to efficiency, yeah? Sorry. This is just about the annual energy produced. So we can use the capacity factor. Okay, 447.15. Megawatt hour. Okay, last part. Suggest a suitable turbine for this application. So to choose a turbine, then we look on the power. Power, 88 kilowatt. We look on the flow, 2.7. We look on the net heat, 4.6. Okay, 4.6 and 2.7. Go back to the table just now. 2.6, this is a lot scale. Sorry, 4 point something. Don't know, maybe here. And flow is 2.6 over here. Okay, and it's 88 kilowatt. So this line is 100 kilowatt, then okay, it's around this area. Okay, so in this area, I can use a cross flow, altimeters, and coupler. Okay, Francis out, the tackle out, belted out. And then based on these 3, you need to pick the correct one. Altimeters is normally one used for power generation, so I think you can cross it. So cross flow and coupler. Okay, but coupler normally will give you better output and it's more widely used as well. Okay, but of course you choose cross flow, I cannot say your normal because based on the table it's still within the range. Okay, so in this case we can use a cross flow or coupler turbine. So you suggest based on the flow rate and the head and also the power output, then the coupler turbine is a suitable turbine for this application. Okay, any question? Okay, then we move to the next one. These are the advantage of the hydropower. Okay, pollution free and green. So do you want to cut off the green? It's no longer green. The operation is green, but the development is not green. So you want to use the word green, then you have to further justify what do you mean by green over here. Okay, it's green during operation, but during the construction of the dam, it's actually generate a lot of carbon dioxide. Okay, next, very high efficiency, up to 95%. Little waste of heat. You do not generate any heat from the system, only a little bit by the friction of the rotation. While the initial cost is high, they are very low cost. Normally, a dam can operate for 100 years. So that although it's very expensive, but it can last for a very, very long time. So end of it, they are very low cost in general. It is very reliable, and the output can be easily adjusted based on the demand without affecting the efficiency. It can be a recreational advantage. Okay, normally the dam can be made as a park, okay, as a recreational park. And then it can be a water storage. You can store the water, and it can be as a flood mitigation. You can control the flood because you control the water flow downward to the downstream. So in other words, you're able to control the flood. And then it's allowed for fish farming. Of course, the dam other than store water, you also can use to farm fish. Okay, this is the advantage of hydropower, and of course, they also have the disadvantage. So first one, it will affect the river marine ecosystem and alter the hydrological cycle. Riverine ecosystems mean that how the fish live in the river. Now you change the water level. Do you know that different type of fish survive and live in the different height or different water level? Okay, some of the fish not able to survive in the very depth water. Maybe because the pressure is too high. Okay, but some of the water river, some of the fish they need very deep water. So if you change the heat or change the water level, definitely will affect the riverine ecosystem. And because when you build the dam, the water level mostly on the upstream will increase, and then the plant or the in the under the sea under the riverbed definitely will not get enough sunlight because it becomes too deep and you are not able to get the sunlight. Okay, and then it's also alter the hydrological cycle. Hydrological cycle is mean that how the water move from the land and ocean surface to the atmosphere and back to the form of precipitation. Hydrological cycle. So now you change the location where you have that water. So of course you change the hydrological cycle. But is this really affect the environment? It's not very subjective. So it means that they maybe will focus on the rain in one point. We don't know because we change the amount of water on different location. Okay, so the evaporation rate on different location also different. So end up with you may cause the very strong rain in certain location and cause no rain at all at certain location. But the effect is very subjective. I don't know how big is the effect of building this, but it definitely will change the water flow rate, sorry, rain flow in certain location if you build that. Okay, and then next, to change the watershed characteristic. Watershed is actually on term of land. Okay, how the land area channel the rain flow back to the sea. Okay, you can see the line, water line. This one we call as a watershed characteristic. But now you build a dam. So the watershed characteristic will also change. Some of the rivers will not have any water left. Some of the rivers will have too many water. Okay, and then dam normally is very far from user. Normally you want to build on the high elevation. And normally human will live at the flat ground. Okay, so it's very far from the user. As danger of dam collapse and flooding, it will have very high capital cost and it's restricted the water flow downstream. Maybe you have the farm and downstream, you need to use the water, but now because you build the dam, then you may not have enough water at the downstream. You will reduce the water level, you will affect the river ecosystem, and you will affect the farming activity at the downstream. Okay, next, reduce the oxygen generation. Okay, you can see that previously all the green area is occupied by tree, so you generate a lot of oxygen. But now you build a dam over here, you build a reservoir over here. So all this area will be occupied by water. So in other words, no tree, no oxygen generation. So you reduce the oxygen generation if you build the dam hydropower. Okay, so this is a disadvantage of the hydropower. But some of them is actually, for example, alter the hydrological cycle, change watershed characteristic, extensive flooding area. These are all actually the short-term effect. Only at the first few years, the dam is in operation. After a few years, everything is already stable. So you will create a new hydrological cycle. You will create a new watershed characteristic. Okay, you just change it, but you not really destroy it. Okay, so it will give the bad impact to some location, but also will give a good impact to the some of the location because here do not have water, then supply the water to the other point. Okay, so the ecosystem, you will have a new ecosystem at the surrounding. Okay, but of course the danger of the dam collapse is always correct. We don't know when the dam will collapse. Maybe by an earthquake or what. Then the water will just release in one shot to the downstream. So definitely will destroy everything. Okay, according to the researcher, these three gorges dam, the largest dam in China. Let me check where is the location. It's at Hubei, China. Okay, you can see that at Yizhang, Hubei, China. According to the research, if the dam is correct, the water will flow from Hubei to Shanghai. Okay. The distance between Hubei and Shanghai is 1,000 kilometers. Okay, but the dam collapse in Hubei will affect the Shanghai. Try to imagine how much water you have in this three quarters dam. So in case the dam collapse, the effect is very, very huge. Okay. Okay, let's continue with this. Another disadvantage of hydropower, there's quite a lot of disadvantage. In flat basin, large dam cause flooding or large tract of land, destroying the local animal and habitat. Okay, because a lot of area around jungle is put under water. People have to be displaced, causing change in lifestyle and custom, even causing emotional scarring. About 40 to 80 million people have been displaced physically by dam movement. So it means that you want to build a dam, mostly the all-asty will be affected. They need to change their lifestyle. Previously, they catch the fish in the river, but now no more river. They have that. Okay, and then the place they stay no longer suitable for stay. So they have to be displaced. Of course, if the displaced we manage correctly and systematically, it should be no problem. You give them enough food, and then you teach them a new way to get the food and money, there should be no problem. But normally, the company, after you build them, it not really care about these people which has been relocated. They don't care about how they make money, how they find the food. Okay, they just make the one-time payment to them maybe. Okay, but and now they do not know how to find the new food because the old method already cannot be used anymore. Okay, so it will cause a big problem for this person. this group of person. Okay, so large amount of plant leaf are submerged and decay anaerobically. Okay, plant life. Okay, so this one decay anaerobically means that it decay in the absence of oxygen. So this in the absence of oxygen, the plant decay will release the methane gas. Okay, if you have sufficient oxygen, normally it will decay or decompose and release carbon dioxide and water. Then still okay lah, just release carbon dioxide. But this one will release the methane gas, more intense greenhouse gas. Okay, it is estimated that a hydroelectric power plant produces 3.5 times the amount of greenhouse gas as a thermal power plant burning fossil fuels. So try to imagine that a hydropower plant, we do not have any burning, but it generates 3.5 times more greenhouse gas than thermal power plant. Okay, but of course, this is just in the first few years of operation because all the plant is now submerged in the water. So they will die, they will decompose by microorganisms. Okay, so whenever they have the decomposition, they will release the methane gas or carbon dioxide, which both of them are very intense greenhouse gas. Okay, so the first few years, definitely the effect is very huge, even more than the burning of the fossil fuels. The next, the migratory patterns of river animals like salmon and trout are affected. These salmon are trout structure. They mostly spend their early life in the river. Okay, it means that when they are young, they spend their life in the river. Then they are the child who spend their life in the river. And when they will swim out to the sea where they live their adult life and gain most of the weight. Okay, so they will grow up in the sea. But when they mature, okay, when some they have matured, they want to find a partner. Okay, they will return to the river to spawn, to lay their egg, to make their second generation. Okay, so but now you build a dam. How are they going to return to their river to spawn and make their second generation? You want to ask the salmon to change their lifestyle. I also don't know how to ask them to change their lifestyle. Okay, so in the Euro country, some of them will make the fish ladder. They will allow the fish to swim outward through the something like this. Okay, so that the other than the dam, there's a ladder for the fish, something like salmon and trout, to swim up to the upstream. Okay, and this will not affect the flow rate. Okay, flow rate of the dam. But of course, you need to quite costly to build this fish ladder. Okay, you can see that maybe I don't know whether there's a real fish or not. This is a good idea that we can consider. Okay. Have a look on this. I think it should be quite interesting. Okay, of course, at this part, the fish cannot swim through the dam. Okay, so they have to make a ladder for the fish. You can see that all these are trout and salmon. Okay, so you can see that they can jump out, they can swim out, ladder by ladder. now they'll go back. You can see they can swim up the ladder. You can see, but if you build the ladder, definitely cannot swim. So you can see all of them jump up the ladder and then go back to their 逆流回合 pursuit. Yeah, it's a very good idea to save the environment. Okay, but most of the dam not really build this kind of the ladder because it's very costly. And even in Malaysia, we don't have salmon, so we don't need to build this. Okay, only at a certain location we have salmon, have to go back from the river for smoke, then they have this. Okay, then the last one is a dam restrict sediment that are responsible for the fertility lands downstream. So because of the sediment is something in the river, can be act as a fertilizer. Okay, so now because you build a dam, all the sediment will not flow down to the downstream, so that the land and the downstream normally will not have enough fertilizer. So the farmer have to use a chemical fertilizer. So actually this cause another problem. Okay, when you use the use a chemical fertilizer. Okay, maybe I'll be that time and show you a little bit about the working principle of Francis turbine. Okay, good. Know that you know what sound actually did. Okay, have a look on turbine. No more
Francis turbines are the most preferred.
This is a Francis turbine. This I say is most widely used turbine in the
hydraulic turbines. It contributes about 60% of the global hydropower capacity, mainly because it can work efficiently under a wide range of operating conditions. Most important part of Francis turbine is its runner. It is fitted with a collection of complex-shaped blades. In runner, water is entered radially and leaves axially. During the course of flow, water glides over runner blades. Francis turbine blades are specially shaped. You can note that blades are having thin airfoil cross-section. So when water flows over it, a low pressure will be produced on one side and high pressure on the other side. This will result in a lift force. You can also note one more peculiar thing about the blade. It is having a bucket kind of shape towards the outlet. So water will hit and produce an impulse force before leaving the runner. Both impulse force and lift force will make the runner rotate. So Francis turbine is not a pure reaction turbine. A portion of force comes from impulse action also. Thus, as water flows over runner blades, both its kinetic and pressure energy will come down. Since flow is entering radially and leaves axially, they are also called mixed flow turbine. Runner is connected to generator via a shaft for electricity production. This arrangement is fitted inside the spiral casing. Flow is entered via an inlet nozzle. Flow rate of water will get reduced along length of casing, since water is drawn into the runner. But decreasing area of spiral casing will make sure that flow is entered to runner region almost at uniform velocity. Stay vanes and guide vanes are fitted at entrance of runner. The basic purpose of them is to convert one part of pressure energy to kinetic energy. Flow which is coming from the casing meets stay vanes, they are fixed. Stay vanes steers the flow towards the runner section. Thus it reduces swirl of inlet flow. Demand for power may vary over time. The guide vane mechanism is used to control water flow rate and make sure that power production is synchronized with power demand. Apart from controlling flow rate, guide vanes also control flow angle to inlet portion of runner blade. Thus, guide vanes make sure that inlet flow angle is at optimum angle of attack for maximum power extraction from fluid. Low pressure at exit side of turbine may cause serious problems of cavitation. So a carefully designed draft tube is fitted at exit side to discharge the fluid out. Draft tube will transform velocity head to static head due to its increasing area and will reduce effect of cavitation. Hope you had a nice session on working of Francis turbines. Thank you.
Okay, so have a look on the comparison between Broughton, Francis, and Kaplan turbine.
Francis and Kaplan are the most commonly used hydraulic turbines. In this video, we will compare these three turbines and see when to use
The
them.
first is the impulse turbine, which is Broughton turbine. Then second, Francis and Kaplan, which are the reaction
turbine. When we move from Pelton to Kaplan, the force-producing mechanism changes from impulse to reaction. In Pelton, pure impulse force of waterjet is responsible for rotation of impeller. Water stored at...
Okay, do you notice that you can see the flow when you hit the blade, it will go to the side. Okay, so this depends on the design of the bracket over here so that it won't block the incoming flow. So this is very important.
Water stored at high altitude can produce high impulse force due to its high velocity. So Pelton turbine are suitable for operation when water energy is available at high head and low flow rate. Whereas Kaplan turbine is suitable for the reverse case. A high water flow will guarantee efficient production of reaction force. So when water is available at high flow rate and low head, Kaplan turbine is the best choice. Francis turbine comes in between for medium head to medium flow rate applications. Francis turbine is not a pure reaction turbine. A portion of force comes from impulse action also. This graph gives a clear idea about when to use which turbine, depending upon available water head and flow rate. It is obvious that Francis turbine covers a wide range of operating conditions, or they can work efficiently in wide range of operating conditions. This is why Francis turbine is the most preferred hydraulic turbine. If you use a turbine out of its recommended operating range, it will work, but less efficiently. It is also interesting to note the direction of fluid flow with respect to axis of rotation in each case.
If you have great people in your organization,
Okay, so this is a comparison between different type of turbine. So I think we still have a few slides left for hydro, so that it will be all for hydro chapter. Okay, so a little bit more. Okay, we'll continue on next week. Okay, any other question?
No questions.
Okay, good. Very interesting. Thank you. Okay, if there's no question, then I think we can dismiss today and see you next week. Thank you for your time and see you and take care. Bye bye.
Thank you, sir.
Thank you.
Thank you, sir.